we're gonna find the domain of multivariable functions. Now, if these were single variable functions, f of x, let's say, then we would want to find out what x values we're allowed to plug into the function and get a real output value for. Since we now have functions of both x and y, we want to find all combinations of x and y that we're allowed to plug in and get a real output. So one possibility is we can test particular coordinate pairs. To do that, all you have to do is plug in a combination of x and y and make sure that it actually does output a real value and it's not undefined. Then you would know that that combination of x and y is part of the domain. That's not always a practical way to find the entire domain, though, because we can't test every combination of x and y. So we have to use some other techniques to try and identify the domain more easily. One option we have is we can actually plot the function in 3 dimensions using an online web application for plotting surfaces. And then we could get a good sense of what the domain is from that. Let's try that technique for the first one, x squared y squared minus 2. Alright, so here is our picture. Alright, so when I look at this one, it appears that there may be whole sections of the xy plane that don't have surface points for them. It's a little tough to tell because maybe the values are just so big that the program can't display them all. And for this function, that would actually be the case. Imagine plugging in any combination of x and y. Would the result ever not have a value? Well, let's take one of those suspicious points right now. Like for example, here, here's positive x and positive y. And if I take the point 10, 10, I'm going to plot that point right now. Okay, 10, 10. I don't see any of the surface in this region. So maybe the function doesn't have an output at 10, 10. What I'll do is I'll actually plug it in. Okay, we're going to have something squared times something squared minus 2. Okay, plug in a 10. It does give me an answer. It's just that the value is so big that it won't be plotted on this display. And the question is, can you think of any two numbers that you could plug in here that would make the result undefined or just not give you an answer? And the fact is, no matter what we pick, -10, -10, you get the same answer. We could try e and pi. I still get an answer. There's nothing that I can't plug in there. So the domain for this function is going to be all combinations of x and y. Now how do we write that? The domain is all sets of x comma y where x and y are real numbers. It's just a kind of a informal way of writing the domain. A little bit more advanced symbolic way of saying it, though, would be r squared. R would stand for all real numbers. But if we want all points in the coordinate plane, we actually want r squared. Let's take a look at the next one, x plus y over x minus y. Okay, this is an interesting function. It looks like we do see pink just about everywhere, but there's one region that we don't see pink, and that's along this line here. Now, why could that be? Could you think of a combination of x and y that if you did plug that combination in, the result would not be defined? Well, one possibility I can think of is, what if x was 0 and y was 0? Then we would get 0 plus 0 over 0 minus 0. That's undefined. So the point 0 comma 0 is actually not in the domain of this function. Okay? Are there any other combinations that might result in undefined? That's undefined too. Let's plot that point. Yeah, or how about 10, 10? It's undefined. Even negative 10, negative 10. All right, so it looks like any time x equals y, that would be a time when this expression would be undefined. Now with this one, we could just kind of look at it and see that that would be the case. But how do we find that result for any fraction? Well, there is a way to do it. What we want is we want the denominator to not be 0. So it's any set of x comma y where the denominator is not 0. So what I'll do is I'll actually take that denominator part and make sure that it's not equal to 0. Rearrange, and you find that x cannot equal y. And that is an expression of the domain of this function. It's all x comma y such that x doesn't equal y. Because if x equals y, the denominator is 0, and that's undefined. So having a denominator of 0 is definitely one big thing that could result in a function being undefined. But there are others, too, that we want to look for in functions. We can't take the square root of a negative, for example. So take this square root of 4 minus x squared minus 4y squared. I'll just plot it real quick, see what it looks like. With kind of a half shell shape here. So yeah, there definitely are going to be some points where we don't see surface. Like, for example, if x is 2 and y is 0, you're good. That point would be right on the edge of the domain, and we can prove that we will get a real value if we just type in an x of 2 and a y of 0. Okay, it does give us a real answer. 0 is a real answer. So 2, 0 is in the domain. But now let's try 2 comma 2. 2 comma 2 is up here in the gray region where we don't have any surface. So, 2 here, and yeah, it's undefined because you're taking the square root of a negative in that case. So we want to find all the points where we're allowed to plug in and find all the points where we're not allowed to plug in. So here's how we could do it. We need the part under the radical to be greater than or equal to 0. That is the requirement for a square root. We could just leave it like that. That's one way to do it. You could rearrange if you want, but just say all x comma y such that 4 minus x squared minus 4y squared is greater than or equal to 0. Now there is a program in Desmos. It is an inequality calculator. There's a link on the page here which would allow you to graph the domain in two-dimensional space. So the domain is going to be on the xy plane. So let's plot the inequality that we had discovered here. All right, so doesn't that look like the projection of our surface that we graphed onto the xy plane? Any set of xy that's within this ellipse would be part of the domain. All right, and so we have one other big condition that we look for, and that is dealing with logs. And so for this surface, we have z equals ln xy. Okay. Notice that we have surface in quadrant 1, and we have surface in quadrant 3, but we don't have any surface in quadrant 2 or 4. Now, the reason why is if we have a negative x and a positive y, then when those two multiply together, they make a negative number. And you can't take the ln of a negative number. But if you do a positive 2 and a positive 2, now you can plug it in. If we do a positive 2 and a negative 2, similarly, we're going to have a problem. So what do we need to do? We just need to ensure that we use all sets of x, y such that the part in the ln argument has to be greater than 0. Not only, you can't take an ln of a negative, but you can't take an ln of 0 either. So for something like that, what does it look like as an inequality? We need the product of x times y to be greater than 0. Now, what this should show, it may not be totally displaying it exactly how we want. We want a dashed line on the horizontal and a dashed line on the vertical. It's not too clear that there's a dash there because we don't want to take any points that are on the y-axis. If they're on the y-axis, then they have an x of 0. And that wouldn't be part of the domain. Okay, so if we're going to draw it, we want two intersecting dashed lines. And we just want to shade everything in quadrant 1, except the axes themselves, of course, and then shade everything in quadrant 3. And that's the domain.